Hey everyone! So today we're going to talk about processes and threads. But let's just forget the textbook definitions for a minute. We're going deeper into the stuff that really matters, the engineering trade-offs. The kind of thinking that separates a junior developer from a senior one. When you really boil it down, every single modern operating system is trying to crack this one huge problem. It's like the master puzzle of computing, right? How do you run a bunch of things at the same time and do it safely and efficiently without the whole thing just, falling apart? In this big puzzle, it really boils down to two main questions. First off, how do we even get multiple things running at once? And maybe even more importantly, how do we make sure that when one of those things inevitably messes up, and it doesn't bring the entire system crashing down with it? And listen, this is not just some boring academic exercise. Seriously, when you're sitting in a systems design interview, nobody's impressed if you can just parrot a definition from a book. What they really want to know is, do you get the trade-offs? Can you actually weigh the pros and cons, the costs and the benefits of a decision? That's the real test. So when it comes to solving this whole concurrency puzzle, it's historically come down to two totally different approaches. You can either build these big, thick walls between all your little bits of work, or you can just let them all share everything. It's really that simple. Isolate or share.
All right, let's look at that first answer, the isolate strategy. This is what gives us the idea of a process. The best way to think about it is like a program running in its own private sandbox. It's totally self-contained. It's got everything it needs to do its job, all packed inside.
So what do we mean when we say its own? Well, it means a process gets its very own private memory space that no other process can even look at, let alone touch. It has its own heap, its own stack, its own list of whatever files it has open. And here's the kicker, the most important part. All of this creates a private failure boundary. And that isolation, that is the single most important thing about a process. I mean, think about it. If one process crashes, let's say because of a bad pointer or something, the damage is completely contained. The OS just steps in, cleans up the mess, and all the other processes just keep humming along like nothing happened. It's a really beautiful, robust design for keeping things stable. But of course, that kind of rock-solid isolation comes with a price tag. And that brings us to the second answer, the thread. A thread is way smaller, way more lightweight. It's a little unit of execution that lives inside a process. This is the share everything strategy in full swing. Okay, so threads inside the same process, they share pretty much everything. We're talking memory space, the heap, global variables, any open files. And because they share all this, talking to each other is super, super fast. The only things a thread really gets to call its own are its personal stack, its own set of CPU registers, and its own instruction pointer. Just to keep track of where it is in a code. But, and this is a huge but, there's a massive trade-off here. Because they share everything, they also share failures. If one single thread crashes, it doesn't just die alone. Nope, it takes every single other thread in that process down with it. The whole thing just evaporates. They live together, they die together. They absolutely share their fate. Okay, so let's recap. We've got processes for isolation and threads for sharing. Seems pretty straightforward, right? Well, not so fast. Now we're going to peel back the curtain and see what's really going on under the hood, at least inside the Linux kernel. Turns out the textbook story you learned, it's not quite the full picture. So let me throw a question at you. When the Linux scheduler is figuring out what to run on the CPU next, what is it actually choosing? Is it picking a process or is it picking a thread? Haha, it's a trick question. The answer is neither of them. Yeah, that's right. Deep down, the Linux kernel doesn't really operate with these two totally separate concepts of a process and a thread like we've been talking about. And here's the big aha moment. In Linux, there is only one thing that the scheduler cares about, and that thing is called a task. That's it. What we call a process and what we call a thread, they're both just tasks to the kernel. The only thing that makes them different is how much stuff they share with the task that created them. This right here, this makes it all click. There's this super powerful system call called clone, and its job is just to create a new task. So when your code calls fork to make a new process, what it's really doing is calling clone and telling it, hey, don't share anything, maximum isolation. On the other hand, when you use something like pthreads_create for a new thread, you're just calling clone and saying, hey, share pretty much everything, maximum sharing. You see, it's not black and white, it's a whole spectrum of sharing. Okay, so now that we have this much better mental model that it's all just tasks and different levels of sharing, we can finally dig into the real-world consequences. Let's talk about performance, memory, and of course, the big one, what happens when things go wrong.
Let's kick things off with speed. Switching from one process to another is, well, it's expensive. The OS has to save all the CPU state, sure, but then it has to do all this other heavy lifting. It's got to tear down the virtual memory mappings, flush the CPU's TLB, which is a super important cache, and that just messes with all the other caches too. It's a lot of work. But switching between threads, oh, that's cheap. It's super fast. All it does is save the registers and swap the stack pointer. The memory address space doesn't change, so none of that expensive cache trashing has to happen.
Okay, how about memory? How efficient are they? Well, the number you see right there is 0. And what's that? That's the number of bytes you have to copy to share data between two threads, 0. Zilch, nada. Because they're in the same memory space, communication is basically instant. One thread writes to a variable and boom, the other one can read it right away. This is what we call zero-copy communication, and it is a huge win for performance. But you knew there was a but coming, right? We always come back to the fundamental trade-off. This whole shared memory thing, it's a total double-edged sword. All it takes is one little programming mistake, a null pointer, a segmentation fault, anything, in just one thread. And the entire process, along with every single one of its threads, comes crashing to a halt. Game over. There's just zero isolation.
And on top of that, this shared memory model basically opens up a Pandora's box of some of the nastiest bugs you can imagine. We're talking race conditions, deadlocks, priority inversion, all the classics. And look, these aren't simple performance problems that you can just solve by buying a faster computer. No way. These are correctness bugs. They're subtle, they depend on timing, and they're an absolute nightmare to track down and fix.
So, after all that, with all these pros and cons floating around, how do you, as the engineer, actually make the right call? How do you decide when to go for the safety of isolation and when to go for the raw speed of sharing?
Well, the guidelines are actually pretty clear once you know them. You reach for processes whenever isolation is your top priority. The perfect example is your web browser, right? Each tab is its own process, so when one of them crashes, it doesn't take down your entire browser. You use them for security boundaries, for running code you don't fully trust, and threads? You use threads when you just need pure, unadulterated speed and really tight data sharing, usually for code you do trust, like in a high-performance computing engine. And out in the real world, the pros often use a mix of both. Multiple processes for that safe isolation, and then multiple threads inside each one to get the work done fast.
All right, so let's say you need to boil all of this down into one killer sentence for that interview. Here it is, ready? Processes provide isolation at the cost of higher overhead, while threads provide efficient concurrency by sharing memory at the cost of correctness and fault isolation. Bam! That one sentence right there, it proves you're not just reciting definitions. It shows you deeply understand the whole shebang.
So there you have it. You can see past the simple definitions now. You get the fundamental trade-off: safety for speed. You understand why things are built the way they are, from the browser on your laptop to the massive database servers running the world. So the question isn't, what are they anymore? The real question is, which trade-off am I willing to make for this problem? Now you have the tools. So what are you going to build?